Hello everyone, welcome to Megger's monthly webinar series. Today's topic is a systematic approach to CT testing in the field. In this session we'll be discussing the basics of CT operation, application of CTs in measurement and protection systems, IEEE recommendations for field testing CTs, and reporting and documentation of the results. My name is Jamie Smith, and I'm the Digital Marketing Specialist for Megger North America, and I'll be acting as the moderator for today's presentation. I'll be supporting you on any technical issues or questions for our presenter during the session. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segment after the presentation. You will receive a copy of the presentation afterwards and a link to the recorded session if you want to watch it again or share it with your colleagues. You should receive that within about a week or two after the webinar. Remember, you can ask questions at any time during the presentation, and I will interject them as we have time. Our presenter today is Vijay.
Don't worry about that.
It's Vijay, and he's an application engineer for relay products at Megger, and he's based out of our Dallas office here. Thank you for joining us, Vijay.
Good morning, everyone. My name is Vijay, and Jamie struggled. My last name is Shan Muga Sundaram. That's a whopping 16-letter last name. So I'm a relay application engineer, predominantly dealing with the relays, protection system, and I'm expanding my territory as well, focusing on some of the CT testing products that Megger offers. During the presentation, if you have any questions or if you cannot hear me properly, just type in and let Jamie know so that he and I are sitting together. So I will try to be as loud as possible and as clear as possible. I have a lot of material to cover today, and what I'm going to do is first we'll start with what all the things that we're going to cover in this presentation. First, I want to start from scratch. For those who don't know much about CT testing, I want to start from scratch, talk about the definition of CT, how it is interpreted in the industry, and I also want to talk about a little bit about the working procedure of a CT. Then I want to focus on the applications, especially what is the mirroring application of the CT and also the protection application of the CT. But most of all, I wanted to focus my presentation on the IEEE recommendations on testing a CT in the field. I want to talk about what all the tests that you can do on the CT, so that's where my main focus of this presentation is going to be. Although the first part of the presentation is more on giving a background information on the CT, how it works and everything. But the later part of the presentation is mostly focused on what are the tests you have to do, what it means by a specific test, how it is done in the industry or how it is done in the field. Finally, I want to talk about some of the procedures or some of the procedures associated with the CT condition assessment, and some of the other things that I want to talk about is reporting and how you can store the results as well. So that's the overview of my presentation. And as I said, I have a lot of materials to cover. Usually I'm a pretty slow talker. But today maybe I have to go a little bit faster than my usual pace. But please feel free to send us your feedback right then and there if I'm going too fast. First, let's start with the definition of a CT. For those of you who don't know, a CT is an instrument transformer, or it's an instrument transformer which is connected in series with the primary windings. So that's what the IEEE standard 100-2000 says. So it is connected in series with the primary winding. The other definition is, again, it's an instrument transformer which transforms the primary current and the primary voltage into a secondary voltage and a secondary current with minimum ratio deviation and also the phase angle deviation. So ideally, we'll go for an exact replica of what it is there in the primary windings. Say, for example, your primary winding can have 1,000 amps flowing through it, but you want exact representation of the primary current on the secondary side. Typically, in the industry, you have either 1 amp or 5 amp on the secondary side. So when you say 1,000:5 CT, which what it means is 1,000 amps flowing through the primary will induce 5 amps flowing through the secondary. Or 1,000:1 amp CT mentions 1,000 amp flowing through the primary. When 1,000 amps flows through the primary, you will see 1 amp on the secondary side. So two things. One is the CT is connected in series with the primary winding, and it transforms the primary values into a corresponding secondary values with minimum phase angle deviation and accurate ratio. Now, what is the purpose of using a CT in the field? That's a very good thing to talk about. One, the first thing that comes to my mind is a CT is used to reduce the value of current, say, for example, 5 amps or 1 amps, as I told you before, at full load, which can be used in the various applications like meters, protection relays, and some other instrumentation as well. Another very important purpose of using a CT is it protects the personnel and also the instrument from exposing it to a very high voltage or a very high value, and keeps it within a reasonable amount of current in each of these applications as mentioned. Now, so when the secondary of the transformer that supplies a current should be an accurate reflection of the primary current, we already talked about that, with a very small phase shift as possible, as little phase shift and as accurate as possible. Now, I want to talk about the basic principles of a current transformer. On an ideal CT, you know that the primary current, or the induced secondary current is the proportional value of the primary current. This is the equation that tells you what would be your secondary current. So in this case, your I2 is equal to I1 times N1 by N2. That ratio, N1 by N2, is typically the ratio of the CT. This is on an ideal CT condition. But when you talk about the real CT, typically, this diagram is a representation of the primary current on the secondary side. That's why you see I1 times N1 divided by N2. So that's the representation of the primary current on the secondary side. And I2 is the actual induced secondary current. The ZB is the load on the CT. And here is the most important component which messes up everything, which is the magnetizing current that flows through the windings of the CT. So that particular element causes, or that particular element is the reason for the losses that occurs in the CT. So typically, your I2, or in theory, your I2 is N1 divided by N2 times I1, which is the primary current representation on the secondary side, minus the magnetizing current. So in reality, it is not possible to neglect the exciting current, or also called as magnetizing current. Now, if I have to represent this in vector diagram, this is how it will be on the right-hand side of your screen. So you have your secondary current, which is your I2, which is nothing but a vectorial addition or subtraction of your primary current represented on the secondary side minus the excitation current, IE. So there you go. You have your ratio, the ratio error that you have to calculate or test, and you also have the phase deviation from the primary to the secondary because of the excitation. So typically, the CTs exhibit two primary errors. One is the accuracy error that is directly dependent upon the gain or linearity, and the other one is the phase angle error. Now, we talked about the basic, how it works, or the basic theory in a CT, how the CT works, and how the ideal CT works, and also how a real CT works. On an ideal CT, we do not consider the excitation current or the magnetizing current that is required by the CT itself. But on reality, it's not the case, and we have to consider that excitation current as well. Now I want to move our presentation to the applications of a CT. So you have the primary side, which involves the circuit breakers, the feeders, the bus, the transformers, and everything. And you have the CT. And where is that CT going to be used? On the secondary side, typically it is used for the protection function, and it is also used for the metering option. So these are the most two major applications of a CT. I would also assume that CTs and PTs are kind of like the sensors of the system, which constantly monitors your primary values and tells you the corresponding secondary values on your system. So you can use it in your SCADA system from the relays, and you can also use it for any other control functions that you want to do based on the readings from the CT. I want to talk a little bit about the different types of CTs being used. As you can see here, we are going to talk more about the uniformly distributed secondary winding. One of the type is called the window type. As you can see, you have a window on the CT. That is where you will provide the primary winding, and your secondary winding is on the core here that surrounds the primary winding. On a bar type CT, you pretty much have the same setup here, except for your secondaries are wound around the core, and your primary goes through the bar here. One of the questions that I have here is asked by Mr. Matthew. He asks, how do you measure the magnetizing current? We're going to talk about that, how to measure the magnetizing current, and how do we calculate the other secondary current. We're going to talk about that in the upcoming slides. Sorry, I'm not answering your question right away, but I will address that question by the end of the presentation, all right? So we are talking about the different types of CTs. One I mentioned about is the window type. The other one is a bar type CT. Now, on the medium to high voltage section, you have different types. One is called a top core type. The other one is the CT with one primary coil, and the other one is a hairpin type. So these are mostly used in the medium voltage and the high voltage CT construction. So you have the top core, the hairpin or the tank type, and the eye bolt type. So this is how you can picturize the CT here. You have the I'm sorry, hold on. So these are the types of CTs that you have here. Typically, here is your CT, and the primary flows through the bushing here. And the secondaries of the CTs are typically connected to your terminals on the terminal box. That might be right here, in the terminal box right here. So the secondary of the CT is accessed through the terminal box or terminal block here, and then you have the bushing that goes that carries the primary. Now, on the application side, I mentioned about the metering option. Where is the metering mostly used? It is typically used to measure the consumption by a consumer. When we talk about a metering type CT, the characteristic of the metering type CT is typically it is more accurate than a protection type CT, mainly because you don't want to have less accurate meter, which directly affects the consumption rate or the consumption measurement of your consumer, or however you want to call it, whether you're a customer or your utility or however you want to call it. So you want to have a more accurate CT in your metering or consumption measurement place. So when you have that kind of a CT, what do you expect from it? You want a high degree of accuracy, anywhere between about 10% or to the 100% of rated current. So you want your metering CT to be very, very accurate. And the IEEE C57.13 indicates that your CT anywhere between 100% of the rated current to the 10% of the rated current, it should have a consistent measurement ratio and also the phase angle, which is typically meaning that your phase angle measurement and phase angle deviation and also your ratio calculation should be accurate anywhere between 100% to the 10% of the rated current, and also at rated frequency. So if you're either 50 hertz or 60 hertz, it doesn't matter, but it has to be within the above said or manufacturer specified accuracy between 10% to 100% of the rated current. Also, another thing that comes to my mind is when you're talking about a metering CT, the metering CT response is typically, the way I would say is the saturation value of the metering type CT is far, far less compared to a protection type CT. And we're going to talk about that as well. While I'm at the metering type CT, I want to talk about the accuracy class tolerance for metering type CT. I'm not too sure whether you guys have seen a picture like this, but I want to explain what this picture means. So this is a graph, this parallelogram is a graph between the ratio correction factor, I want to talk about the ratio correction factor as well, and the power factor, the phase angle either leading or lagging. So this inner box represents the accuracy class of a CT. So you expect when you draw a graph between your ratio correction factor and your phase angle, you want your CT to respond between this parallelogram or the rated current. For a 10% rated current, that's your middle parallelogram, and you want your CT response to stay within this limit for a 10% rated current. And for 100% rated current, you want that the response from the CT to stay within that very narrow inner parallelogram. Now, when I say you have to draw a graph between a ratio correction factor and the phase angle, what does it mean by a ratio correction factor? That's the first question that comes to your mind. Now, the ratio correction factor, also termed as RCF, ratio correction factor, is nothing but a ratio between the actual CT ratio that you measure, and we're going to talk about how to measure the CT ratio and everything. So your measured CT ratio to the nameplate ratio as mentioned by the manufacturer himself. So you can also say your actual ratio is nothing but a nameplate ratio times the ratio correction factor. But when you draw a parallelogram, or when you draw a graph between the ratio correction factor and the phase angle, for 100% it has to stay within this narrow limit. For 10% it should stay within this for 10% it should, for 10% rated current, it can deviate a little bit, but not so much. This particular outer parallelogram is for 0.6% accuracy class, and I'm going to talk about what is the allowed accuracy, or what is the allowed accuracy when we talk about a 0.3 accuracy class or a 0.6 accuracy class for metering type CT. So this slide pretty much contains the same thing that I mentioned before. So for a standard burden, when I say standard burden, a burden is nothing but how much load you provide on the CT itself. So that's the burden on the CT. Or in other terms, how much resistance is offered by the circuit connected to the CT to the flow of current through the CT secondary. So that's called the burden of the CT. And for a rated burden, 10% to 100% of the rated primary current, your CT ratio should be within the specified limit. So if you see here, the standard accuracy class for a metering type CT, when we say 0.3 or 0.6 or 1.2, whichever it is, at 100% rated current on the primary side, your secondary side measurement should not deviate more than 0.997%, or in other words, 3% plus or minus 0.3% of the rated value. And at 10% of the rated current, you can have up to plus or minus 6%. For a 0.6 accuracy class, you have to say, or you can say that at 100% rated current, it should be within plus or minus 6%, and at 10% rated current, it should be plus or minus 12%. And that same goes for 1.2. It has to stay within 12% for the 100% rated current, and also it has to stay within 24% at 10% rated current. I know it's a lot confusing when I talk about percentage in every single word. Forgive me if I'm going a little too fast. I have a lot of material to cover within the hour. And this is not something that I want to focus really on. I want to focus more on the testing procedures. This is some background information that I want to provide on the metering type CT and the protection type CT, what exactly it means by when we say it is a 0.3 accuracy class or a 0.6 accuracy class. Now, talking about the standard burden, the burden design is nothing but the impedance offered by the CT circuit on the CT secondary itself, which is typically represented by Z. Again, it's nothing but R plus J omega L, the resistance and reactance. Now, as I told you before, the burden is typically represented in terms of VA, which is nothing but V times the secondary current via V times IS, as mentioned here. V times IS, and which is also equal to I squared of the secondary current times the impedance offered by the CT circuit on the CT itself. Now, if you think about it, the secondary current is typically either 1 amp or 5 amp. As mentioned before, it's either 1 amp or 5 amp. So that is nothing but 5 square times a burden designation for a 5 amp secondary CT, or 1 square times burden designation for a 1 amp secondary CT. Power factor is measured or calculated as R by Z. Now, if you say a burden designation of B-0.1, which means that a resistance of 0.09, inductance of 0.116. That's the R plus j omega L value. That's 0.09 plus j 0.116. So the overall impedance is 0.1, and the VA rating is 2.5 with a power factor of 0.9. That's calculated from here. So this is a table of standard burdens for a metering type CT. And again, you can always come back to this presentation. The presentation is given to you at the end of, as Jamie said, probably a week or two later. So you can always come back and see these graphs as well. Although I want to focus more on the application first and then be done with it, I want to talk more about the protective relaying application. One of the other major applications of the CT is the protective relaying. As I told you before, I would consider the CTs and PTs are like the eyes of a power system, where it constantly monitors your current flowing through the primary and also the voltage on the line. So since you measure the voltage and current on each and every single line in each and every single node, you're pretty much calculating the power, the P, Q, S, what else? Power factor, pretty much everything associated with the power system. That can be used in your load flow analysis, whether your system is stable or not stable, whether you want to isolate a system because your system is unstable, what kind of place you want to, or what kind of system you have to isolate. So you're completely monitoring your power system based on the readings from your CTs and the PTs. For me, this is one of the major sensors of your power system as such. And one main application of the CT is, as I told you before, is metering, and the other thing is protection. I also mentioned that your metering type CT should be more accurate because that is what calculates the consumption by any consumer. On the protection side, it doesn't need that accurate as a metering CT. But it does not mean that it need not be accurate at all. It has to stay within about a 10% range, anywhere from 1 to 20 times the rated current. That's what is mentioned by the IEEE C57-13. It mentions that the accuracy of your protection type CT should be within 10% from anywhere between 1 to 20 times the rated current. Why 20 times if you think about it? When there is a fault, for example, let's say there is a line to ground fault, naturally your fault current increases, your fault voltage decreases depending upon how your fault impedance is. So that's an example for when the current can go beyond the rated current. So you're pretty much shorting your power supply. Your current is supposed to go higher because there is no resistance offered to the flow of current. So that's why, and another example that I can think of on top of my head is when you charge a transformer, for example. When people say, or it's a general industry practice that when you charge a transformer, the rated current, the current that is flowing through the transformer is anywhere between 5 to 15 times during the initial cycle. So that's the transient current consumed by the transformer itself. So your CT should be able to withstand, your protection type CT should be able to withstand that much amount of current, and also translate the primary current as accurately as possible within that 5 to 15% of the value during transformer charging. So that's one of the reasons why IEEE says in the standard C57.13.1 says it should the response of the CT should be within anywhere between 10% or within 10% for the range of 1 to 20 times the rate of current. Now, another major important thing is the types of CT for a protection class, protection application. One is called a class C, and the other one is called a class T. What it means is, on a class C type of CT, the leakage flux, I talked about the magnetizing current, and I'm going to answer Mr. Matthews' question as well. So the leakage current that is on the CT or on the core of the CT is negligible on the class C type. So you can calculate the ratio of the CT. But on a class T type, the magnetizing current or the leakage flux in the core is appreciable. So you can have the ratio, you can have a 1% ratio difference between the actual ratio and the calculated ratio. So a class T type CT has to be tested for the CT ratio. Another thing is the relay accuracy class. Some of the typical numbers that you might see on a CT when you're doing a testing on a CT is something as given here. This is an example. 10C800, what does it mean? Here the 800 means, the 800 here means the maximum secondary voltage developed at about 20 times the rated current without exceeding the plus or minus 10% ratio error that we mentioned. So that 800 means the maximum response in terms of voltage, the maximum response from the CT at about 20 times the rated current. C is again the leakage flux on the core is negligent, so you can calculate the CT ratio, and the 10% means what is the maximum expected ratio error at about 20 times the rated current. So when we say 10C800, it means the secondary current, the secondary voltage, the induced secondary voltage is at about 800. That's the maximum value. When we say 10C400, the induced secondary current, secondary voltage is about 400 volts. Similar to the metering type CT on a 5 amp secondary winding, these are all the burden calculations. For a B1, the resistance is 0.5, the inductance is 2.3, so the overall impedance is 1 ohm, with a VA rating of 25 and a power factor of 0.5. As I told you before, you can come back to these tables and verify it at a later stage as well. I want to proceed next to the graph here. So if you draw a graph between the secondary terminal voltage that's the induced secondary terminal voltage on the CT secondary to the applied CT amps at 100 amps, which is like the 20 times 5 is 100. So 20 times the rated current, the induced voltage is at about 800 for a C800 or T800 CT. It's about 400 volts for C400 or T400, and so on and so forth. This is for a 5 amp CT. Now, this is the main part that I want to focus on, testing of the CT, what all the things that we need to do on testing of the CT. before that, I want to say, why do we test the CT? That's the main question that comes. Hey, why do I need to test the CT in the first place? This is why. So CT explosion is a major reason, and I'm going to talk about the reasons behind why this can happen. So your CT can burn, your CT can explode, your CT can do whatever it needs to do when you're supplying faulty current into the relay. Now, the rest of my presentation is based on two things. One is an IEEE C57-13, which talks about the standard requirement for instrument transformers. The other one is IEEE C57.13.1, which is nothing but a guide for field testing of relaying CTs. So one of the things is, if you go to conferences like PSRC, that's one of the IEEE group. I'm a part of the C57.13.1 working group, which talks about the guidance given by the IEEE for testing a relay CT in the field. So my other half of the other part of the presentation that I'm going to do is mostly based upon the standard from IEEE. Before going through this, I want to talk about the safety. There are two kinds of people, right? One which follows the procedure and follows all the things for safety, as mentioned or as shown on the left-hand side. And on the right-hand side, those are the imaginative people. Do not do that. Don't try this at home. So before going through the procedures for field testing and CT, I want to mention about the safety. There are a couple of things in terms of safety. One is, if you are a testing engineer, make sure that you protect your personnel and the equipment which is in the close proximity. And also, please follow the local safety policies and the instructions, because each company can have different safety policies and the safety procedures. Like, you have to let some person know within the company before you can even start doing testing. So make sure that you follow any of the local safety policies and the instructions as given by the company that you're working for, or follow whatever safety procedures that they mention to you. Third thing is, before you test, make sure you have the grounding system properly, or you ground the system properly, and also you follow all the grounding procedures as well. Finally, make sure that you isolate the system that you're going to test from any potential energization before or during the testing. Make sure you isolate the system properly as well. I cannot stress more on the safety procedures that you have to follow. Now, going forward, I want to focus on what are all the tests that you can do on a CT or any type of CT. As mentioned by IEEE, you have to do insulation resistance test, a winding resistance test, excitation, or also called as a saturation test, a ratio test, phase deviation, polarity test, and finally a burden test. Most people do the burden test when they are doing a commissioning of a CT. I haven't seen many people doing burden tests as a part of a periodic maintenance of a CT. But I've seen people doing the top portion, like the insulation resistance, the winding resistance, the excitation test, the ratio, and the phase deviation, also the polarity test. as a part of a periodic maintenance. Now, what do we recommend as a testing sequence? If you think you enter the nameplate data, or you make a note of the nameplate data as mentioned on the CT by the manufacturer. And then you start doing the insulation resistance test, followed by the winding resistance test, which is on the secondary. Then the third thing is demagnetization. There is a reason why we do the demagnetization test, and I'm going to talk about that as well, the following slides. Followed by the excitation or the saturation test after the demagnetization test. And finally, you do the turns ratio and the polarity test. After you finish all these tests, you're going to do you're going to record all the data that you get from the CT and generate a test report. Now, I want to talk about the insulation resistance test. For those of you who don't know how the insulation resistance test is done, in the industry it is commonly called as Mrct test, the insulation resistance. And the way you do that is you short, as shown in this picture, you will short the high side and also you will short the secondary side with the ground, and then you pass or apply voltage across these terminals and measure the leakage current. So you have the applied voltage and you also measure the leakage current. If everything is isolated properly, or in other words, if everything is insulated properly, like when the secondary is insulated properly from the primary and the ground, you will not see too much of a leakage current. Your current will be very low, and your applied voltage will be higher. Typically, you will apply either 500 volt or 1,000 volt, depending upon how much your relay can, how much your CT can take. Again, I'm a relay application engineer, so first thing that pops to my mind is relays. So how much your CT can take. So your voltage is at about, let's say, 1,000 volt, and your measured leakage current is very, very low. Naturally, by Ohm's law, what do you expect? The impedance or resistance. What do you expect? You'll expect a very high value. What does the IEEE standard say about this? The standard C57.13.1 says your measured resistance value should be compared to any other device with the same rating and same everything. And if your readings are lower, then you have to carefully investigate why it is lower. What is the lower value? What is the lower value? I don't know about that. If you think about that, anything less than 1 mega ohm is a lower value. One of the most common reasons, if you think about it, why the insulation resistance could be low is because the presence of moisture, and as IEEE says, or IEEE recommends, that when you're doing the insulation resistance test on a CT and you're receiving a lower value, probably one of the common reason is because of the presence of moisture. So you have to dry out the CT and then redo the test on the CT for insulation resistance. So first thing you might do is dry the CTs out and then do the test again. So the first test that we are talking about, insulation resistance. Now let's move on to the winding resistance. As you can see on the right-hand side, you have the winding here. What you do is you inject a test current into the winding and you measure the voltage drop across this winding. So again, you're going to use the Ohm's law to measure what is your resistance offered by the winding itself for the flow of the secondary current. Typically, it is a DC test. So you will apply a DC current and measure what is your DC voltage drop across your winding, across all the secondary windings. One of the problems that is associated with this winding resistance test is when you apply a DC across the CT, you are running the CT, or there is a danger of magnetizing the CT core itself. Magnetizing means you're aligning the magnetic field in a certain direction on the core. So what you have to do is the IEEE C37.110. It's a different number than I've been telling you from the start. So C37.110 recommends that once you finish the winding resistance test, you have to demagnetize the CT. Most of you would have seen this picture. Excuse me. Most of you would have seen this picture. This is the BH curve. So BH curve is nothing but a graph between a flux density, the density of flux on your core, and H is your magnetizing force, the force that is creating the magnetization of the core. So when you draw a graph between your B, the flux density, and the H, the magnetizing force, so this right here is called coercivity. So even the presence of the magnetizing force with no flux density, zero flux density with some magnetizing force, that's called coercivity, and retentivity, which is the presence of flux density for no force. Nobody is pushing it, but still there is a flux present on the CT core. So both are bad. So what you do is you gradually increase the voltage, the secondary voltage, by applying current, or you apply voltage and you measure the current. You gradually increase the applied voltage across the secondary and push it into the saturation area, completely saturated, and then you slowly reduce it and bring it to the 0 point here. So you saturate it completely and then slowly bring it down or demagnetize to the 0 point, and this process is called demagnetization. Now comes the excitation or the saturation current, saturation value. And hopefully this should answer the question from Mr. Matthew. So what you do in an excitation or the saturation test. So you're going to apply voltage on the secondary winding, and you're going to measure the current that has been induced or that is flowing through each and every single tap on the secondary. You can have a 5-tap CT, a 2-tap CT, or whatever number of taps you can have. Most predominant 1 or 2 tap are, I would say, single tap and 5-tap CT. So based on this measurement, you're going to draw a graph between what is your voltage applied and the measured current, and you draw a graph between those two values. So on your y-axis, you have your secondary excitation volts, and on the x-axis, you have the secondary exciting amps on this. So for lower values, remember you are doing a demag before doing this test. So your response will be a linear line to a certain level, and then it starts to saturate. I want to go back to this particular diagram. So I talked about this. So the response from the CT is pretty linear until its own saturation point, and then it starts to saturate, which is nothing but no matter what voltage you provide, the corresponding current is going to, no matter what is your excitation current, your response from the CT is going to be pretty much the same, which is constant. And for C800, it is somewhere in the range of 800 volts. for C400, no matter what your excitation current is, or the current through the primary is, or the induced current on the secondary is, man, I'm giving you guys a lot of options. However you want to think, primary current, higher primary current, or the induced secondary current, no matter what it is, your response from the secondary is going to be constant after a certain value. That's why it's called, hey, the CT saturated. It is not going to do anything anymore. So that's the saturation test. You apply voltage and you measure the current on the secondary on each and every single tap. So this is your response. This is your typical response on each and every single tap. So now let's move on to the ratio test. There are two types you can do the ratio test. One is the voltage method and the current method. On a voltage method, what you do is you supply a suitable voltage, typically below the saturation. So if you look at the curve, you're going to supply a voltage somewhere in between this range, in the linear range, in other words, in the linear range. So anything beyond this value, you're not going to see much of a change on the induced secondary voltage. So you don't want to do a ratio test in this range. This is called knee point. Beyond this, there is the response of the CT is not true. So you're going to supply a value in this range, and typically it's about 30 to 40% of the knee point value. 30 to 40% of the knee point value. So you're going to supply about 30 to 40% of the saturating value, and then you're going to measure the corresponding current. You're going to measure the corresponding primary voltage. You apply voltage across the secondary below the saturation value, and you're going to measure the voltage on the primary. So now you can take a ratio between the primary and the secondary, and that is typically your ratio of the CT. You can also do the same test using current values. You apply a suitable current, again, less than the saturation value, and then you measure the current across the primary. That typically gives you the ratio of the CT itself. Sorry, I'm running out of time. I think I have like about eight minutes, so I'm partially rushing through my content here. So polarity test, make sure, you know, as a law, the current entering into the pole is equal to the, is proportionately equal to the current exiting the dot. So you have to test that. So at the same instant of time, the primary current entering the terminal of the primary and the secondary current exiting the secondary should be proportional to each other. So that's one of the very main reasons why you do a polarity test. On top of my head, I can think of what could go wrong if you connect H1 to the H2 terminal and H2 to the H1 terminal. What could go wrong? The secondary response is going to be in the different direction, so which is like 180 degrees out, or in other words, completely in the opposite direction. When you have a differential operation protecting your transformer, your generator, your bus bar, your feeder, whatever it is, not feeder, but typically the generators, your transformers, your bus bars, the differential operation is going to see a differential current, and it is going to say, hey, please isolate the system. What's the problem with that? Well, let's say, for example, on a generator you misconnected or wrongly connected the polarity of the CT. So it's going to trip on a differential operation, and the differential operation is on a generator is considered as a Class A trip, and it means that something is very wrong with the generator. And you're going to do a lot of tests on the generator before you start the generator again. So that's going to completely stop production of the power for at least a long time. So make sure when you do the commissioning and or also your periodic maintenance, make sure you do the polarity test and it is a pass. So this is how you do a polarity test. You jumper the non-polarity terminals and apply voltage. Make sure that you're measuring the current appropriately. Now I want to move to burden test. Again, I'm sorry I'm rushing through my presentation a little bit because I have less time. The final thing that I want to talk about is burden test. Burden test is typically done during commissioning. I haven't seen many people doing burden test during a periodic maintenance, but there are also utilities which recommends doing burden test every now and then, or whenever there is a change in their system. For example, they might have added a new system in their existing substation, or they could have added something that would affect the burden, so they'll do the burden test during periodic maintenance as well. As I told you before, it is typically expressed in terms of VA, volt amps, and power factor at a specified current value. And it is the tester or the test engineer's duty or commissioning engineer's duty to make sure that the burden on the CT remains less than or within the range of whatever the manufacturer specifies. You cannot have too much burden on a CT and expect it to provide you accurate results from the CT. We talked about this before. This is the vector representation of why there is a ratio error and also a phase angle error. Typically, it should be well within the range, and we talked about the parallelogram as well. So it has to stay within the range as mentioned by the manufacturer. For a 0.3 accuracy class, it has to remain within 0.3 value between the ratio correction factor and also the phase angle. Now, one of the other major thing is how do I test my CT, which is on a delta winding of a transformer? So let's assume that your CT is on the H1 bushing of your transformer. How do you test it if the transformer is connected on a delta winding? So the first step here is you short all the secondaries of the transformer. You short all the secondaries of the transformer, and then you also short the terminal which is not being used by the CT here. So if it is on the H1, you're going to short the H2 and H3. And the third thing that you would do is you connect the primary side from H1 to the H1 terminal of the transformer, and from the CT tester you connect the H2 to the H2. Also, you will connect the CT secondary to the CT secondary as mentioned on the CT tester. It could be any CT tester. So, and then on you are going to do all the tests, pretty much follow all the tests. As we mentioned before, you're going to do insulation resistance, winding resistance, demagnetize the CT, and then do excitation test. Maybe I have to go here to understand properly. So you're going to do an insulation resistance, winding resistance, saturation test, ratio and phase deviation, polarity test on the CT, on that particular CT. Oops. So this is for H1. What we have done here is we have made a table of how to do the CT testing if the CT is on H1 bushing, H2 bushing, and H3 bushing. What all the things you have to jumper, and how you have to connect your H1 test leads, H2 test leads, X1 and X2 test leads to the CT. Since we are running out of time and I have about 10 other slides, I will request you to come back to the presentation. Just take a look at this table so that, when you're doing a CT testing on a delta winding, you will know what to jump and how to connect the CT test leads. on a Y-type CT or on Y-winding transformers, how do you connect it? First thing you will do, or when you're doing a secondary, which is secondary of a transformer, which is a Y connection, you are going to short all the primary, H1, H2, and H3. You're going to short it. And then the second thing is you're going to connect your H1 to X1, H2 to X0, which is the neutral. So the CT lies between the X1 bushing and the X0, and you connect your secondary terminals here. So, and from then on, you're going to do your testing, or all the 5 tests that we mentioned before. Again, we have made a table that includes what all the things that you need to jumper, and when you're doing an X1 bushing CT, how are you going to connect your test leads as well. This is a pretty straightforward table, not too complicated. The picture itself should explain most of the things that we put down in the table. So please do come back and take a look at this table if you have time. Now, quickly, I want to talk about the traditional method of testing CT. Typically, what you do is if it is a window type CT, you're going to pass through your H1 and H2 lead through the window. So this is your primary, and make sure the polarity is right. And you connect your secondary, the secondary windings, to the X1 and X2 terminal of your CT test equipment. There is a method called non-concurrent CT testing method, and what you're going to do is you're going to repeat the same thing here as mentioned, except that your primary winding doesn't change much. Only thing is you're going to connect all your secondaries to the secondary terminals. So as you can see here, your X1 is connected to X1, X2 is connected to X2, so on and so forth. So you do all the 5 tests one by one on each and every single terminal. So you take the terminal X1, you do all the 5 tests. You take X2, you do all the 5 tests. X3, X4, or X1 to X2, X1 to X3, X1 to X4, X1 to X5. You do the test one by one on each of these things. What we have come up with is we have advanced technology on our test set, and that is testing all the 5 taps at the same time with concurrent measurements on all 5 taps. So you do the 5 tests as mentioned on all 5 of the 5 tests on all 5 taps at the same time, or how many number of taps you have at the same time. When you do the test, we did the test here, and we saw, hey, are there any differences between, when you're doing a non-concurrent test, which is typically an older method of doing it, and a concurrent test, which is a newer method of doing it, or an advanced method of doing it? Are there any differences? And we observed that there's no difference when you're doing a saturation test. This is between X1, X3, X2, X3, X2, X4, and X2, X5. Ratio test, pretty much as you can see, there's not much of a difference between a non-concurrent test and a concurrent test. If you see, the ratio error is less than 0.0, or somewhere in the 0.001 or 0.01 range. That's negligible. We did the winding resistance test as well, and we didn't see much of a change in there. So we pretty much did all the tests here with non-concurrent and concurrent methods, and did not see any changes. So here's my conclusion. What we have covered during this presentation is we quickly went through the basics of CT. We talked about the definition of a CT. We talked about the different types of application of a CT. One is a metering type, and another one is a protection type. as naturally your metering type CT is more accurate and your protection type is more withstandable in terms of saturation. Your metering type has a lesser saturation value. Your protection type has a higher saturation value. We also talked about the different tests that you can do and a specific procedure that you can do or that you have to follow when you're doing a CT test in the field. First, you have to start with insulation resistance. Make sure that the insulation between your primary and secondary, your primary and ground, and also the secondary and ground is intact. Then you will do a winding resistance, and then you will do a demagnetization, followed by a saturation test and the polarity ratio test. So that's all you do. So there is a whole test sequence that IEEE recommends, and I would assume that you also follow the safety procedures that we mentioned. Please make sure that you are following the safety procedures before you start doing the test, and you also follow the procedures as mentioned by IEEE C57-37.1 procedures. At this point, I really appreciate spending time with you guys, and I really appreciate your questions. Thanks for tuning in, and I'm going to transfer this to Mr. Jamie.
Hi, everyone. I just want to say thank you to VJ for presenting the webinar. At this time, the webinar is officially concluded. Based on feedback from last year's sessions, we're going to extend the Q&A session for another 30 minutes to answer all your questions, or at least try to answer all of them. If you have any other questions, please submit them now in the Q&A box. For those that are leaving, when you close the webinar window, a survey should pop up on the screen. We would greatly appreciate it if you could take a couple of minutes and just provide some feedback so we can continue to improve these webinars in the future. A copy of the presentation will also be emailed to everyone in the next few days. That will include a recording of this session, which will also be available on the website at megger.com/webinars, and that should be up within the next week or two. Our webinar landing page also contains the schedule for all upcoming webinars and recordings of all previous webinars. And usually, also, if you follow us on any social media, Facebook, LinkedIn, we always provide updates on the upcoming webinars, so it's good to follow us on there as well. If you're looking for any webinar-related information, again, the URL is megger.com/webinars. All right, now let's get to some of your questions. We had about 15 to 20 questions, so we're going to try to get all those answered. The ones we can't get to within 30 minutes, and we will reply to you personally, and we can send the answers to everyone as well.
So the first question, I'm not too sure whether I answered. Oh, by the way, this is VJ again. So how do you measure the magnetizing current? So you have the ratio as mentioned by the manufacturer. What you do is you apply primary voltage, you measure the secondary voltage on any of the tabs. Let's say your primary is 1,000 to 1, or your ratio is 1,000 to 1. So you apply voltage on the primary, or you can also go for a current method. You apply voltage on the primary, you measure the voltage on the secondary. Ideally, it should be the same. When if you measure the ratio, it should be 1,000 to 1. But whatever, you're not going to measure 1,000 to 1 ratio. There's going to be a difference. And that difference is directly a contributing factor to the magnetizing current. So that's why, or that's how you measure the magnetizing current. Now the next question is, are separate CTs usually used for metering and relay circuits? In other words, relays and meterings are not mixed in the same CT circuit. Mr. Steve Lockyer, Mr. Steve, those are separate CTs. but it can be on the same CT circuit. For example, in one of the bushings, I have to go back to the presentation. Okay, so if you look at the picture here on the left-hand side, you see a bushing, and inside the bushing, it has typically has two CTs. One is for metering type, the other one is for relaying type. So the CT circuit is pretty much the same, but the CTs are different. One is specifically for metering application, the other one is specifically for relaying application or protection application. Now, third question. Oh, so what is a 10C400 CT? What is the 10 before class C? Mr. Mohanraj Arcad Fiddle. So, hold on. I'm sorry if I was going through a little too fast on the slide. So this 10 first thing here mentions the maximum ratio error at 20% weighted current, as mentioned by the manufacturer. So some of the CTs could be really accurate even at 20 times the rated current. So that first number typically means that what is the maximum ratio error at 20% rated current. So another, okay, this is a very interesting question, Mr. Marcelino Astillero. Please show or explain how to test the burden function of a Megger Mrct. Might have to go to the so the way you do the burden test on a CT circuit is pretty much you're going to connect your CT secondary, or you're going to disconnect your CT secondary, and you're going to directly inject voltage on the CT circuit, and then you're going to measure the current on the CT circuit. So now you have the voltage and also the current values, and that should give you the burden, or in other terms, the impedance of the CT secondary circuit, not the CT secondary, but the CT secondary circuit on the CT. I'm going to show you a picture of how it is usually done on the Mrct. So here, if you look at this picture, you have the X1 and X5, which is the CT secondary. What you're going to do is you're going to disconnect it. You are going to, from the test set, you're going to connect the X1 source and X5 source across the CT secondary circuit itself. And then you're going to measure, or you're going to connect H1 and H2 across the burden as well. So this is going to apply voltage, and you're going to measure the current across flowing through the burden. And that's how you calculate the burden on the CT secondary itself. Another question, Mr. Nuno Montero. During the insulation test, does polarity matter? does it play a role during an insulation test? My straight answer would be no. It doesn't matter during an insulation test, because what you're doing is during an insulation test, you're pretty much measuring the you're just applying voltage and you're measuring the current, or you're measuring the leakage current. So the presence of leakage current is what matters, not the direction of the leakage current. So, as I told you during the presentation, the leakage current is going to be very, very low. It's going to be a very low value, and that's why you typically see insulation resistance value above 1 mega ohm. Lots of questions, Jamie. Well, there's another question. What is the best method for field drying the CT for low resistance? I don't know the answer, sir. Mr. Douglas Baxter, I don't know the answer, but probably what I can do is I can ask some of the senior application engineers here in Megger, and I can get back to you on the answer. I also see a lot of questions, something similar to that. If I don't know the answer, probably what I can do is I will get back to you with the answer, and because probably I may not be comfortable answering the question because I'm not 100% sure. One other question is, well, this is an interesting question here. So, which test is giving you indication that the CT shall fail soon and must be decommissioned? Well, I would assume this is a very interesting question. On what basis you decide whether the CT is going to go bad and you have to replace it? If I have to think about it, if I'm the testing engineer and if I have to make decisions based on that, I'm going to do I'm going to do winding resistance and insulation resistance test. That gives me a very good idea of how the insulation on the CT is, and is it deteriorating, or is it something internally wrong with the CT? There are very interesting scenarios where the CT was still working when the insulation had completely melted, and there are instances as well. So depending upon my insulation resistance test, I will have a better idea of whether the CT is disintegrating or not. And also, the ratio test gives me a better idea of whether I have to use it in the first place or not. If it is a really bad CT ratio result that I'm getting, then there's no use of me using it in either application, whether it is a protection application or a metering application. I don't want to use something which is beyond the tolerance value, and that's one of the reasons why you do the parallelogram here. So you do the parallelogram, or first you do the actual CT ratio. You get the measured CT ratio, and you're going to calculate the RCF factor, or RC factor, the ratio correction factor. And from that, you also will measure the phase angle, whether it is leading or lagging, and based on that, you're going to draw a dot on the parallelogram. If it is within the parallelogram, which means that it is working in a good condition. If it is not, then it is not working in a good condition. So based on these results, the ratio correction factor and also the insulation resistance, you can determine whether it is approaching its end of life. Oh, another very good question, Mr. Bikram Chaudhary. Is there IEEE or any other standard recommendation how often CT needs to be tested? Yes, there is a recommendation from the IEEE standard on how often or what is your, hold on, I have to look for the presentation. So how often you have to test your CT. And that was another presentation that I made. I can find it. You know what, I'm sorry, I couldn't find the presentation, but it's typically of the CTs, you have to test it every 12 years. I want to say 12 years, but I'll definitely get back to you on this question. It is recommended that you test at least every 12 years, but I've seen industry testing every 3 years as part of their maintenance program. So Jamie, there are a lot of other questions, but not too much time. So
I'll do a couple more. I think we still have time for a few more.
okay. Oh, we have 10 minutes? Okay. Because it's showing here is an hour and 30 minutes, and I'm already past that. Can I get a copy of the presentation? Mr. Tom Boyle, yes sir, you will get a copy of the presentation from the website. I think Mr. Jamie mentioned about how to get the copy of it. I think you will receive an email, I guess.
Correct. I'll email everyone with a copy of the presentation.
What's the maximum VA of your MRCT? The maximum voltage that you can apply from an MRCT is 2,000 volts. There's not a VA rating that I know of. I can get back to you, Mr. Manuel Hapte. So how do you perform your, this is another question from Mr. Dustin Peak. How do you perform insulation resistance on a window type CT? For example, where do you place your testing leads? I want to go back to the software here. I'm not too sure whether you're seeing the software pages I see. So if you're doing what is insulation resistance test? So when you're doing an insulation resistance test, typically what you're doing here is, this is how you connect. You connect your X1, X2, X3, X4, and X5 to the respective tabs. I think I'm showing you a picture of only 2 tabs, but you can connect all the other tabs as well. The primary side is connected to the primary winding here, the H1 and H2, and your voltage injection source, which is the X1 source and X5 source, is connected across X1 and X5. So when you're doing an insulation test, the shorting, as mentioned in the, I have to go back to this picture, sorry. Let me go back to this picture, yeah. So the shorting of the H1 and H2, X1 and X2 with the ground happens internally on the test set. At least from an Mrct that I know of, it is done internally. You don't have to do any connection changes, none at all. So pretty much you will connect your high side to the high side, your secondary side to the secondary side, and then the switching or the shorting is happening internally. And this ground is the third leg of your input connection, or the ground of the CT itself, sorry, the CT tester itself. So that is also taken care of internally. I think this should also answer another question from somebody else I saw. I'm sorry, the screen is so small, not able to see all the questions properly. This also should answer another question which was pretty much asking the same thing. So Mr. Dustin, I think there's no need for you to change any connection after you do it one time, which is connecting your primary side to the primary test leads, your secondary tabs to the secondary test leads, and then you're pretty much done with it. All the connection changes are done internally based on an Mrct that I know of. Oh, this is a very, very important question from Mr. Tony Pino. Does the device determine good or bad test results with just a pass or fail? This is a very good question. When I started learning about the software, or about the hardware, I asked pretty much some of the experts we have here the same question. Hey, how do I know whether the test result is a pass or a fail? Let me go to one of the test results. So let's assume that you do the testing. You do the ratio test, you do the saturation test, you do the winding resistance and insulation. I can say when the winding resistance is about 1 mega ohm, yeah, it is a good, the winding resistance is good. I can say, yeah, that is good. But let's say you do the insulation resistance, you do the saturation test. One time you do the test for a C800 type CT, it comes back and say the value, the knee point value is, for a C800, it says 796, which is pretty damn close to a C800 or 800 volts. It's a pass. The next time you do the test, it's going to be a different value. It's not going to be 796 again. It could be 812. Is that a bad value? No, it's not a bad value. It is somewhere in between 800. We can do algorithms to look at the knee point and say if it is anything beyond a certain 5 to 10% of the value, it's a fail. But again, even a 750 volts response from the CT is not a bad value. It just depends on how you did the test and what results you got from the test. So to answer your question directly, our software does not tell you whether it is a good or a bad CT. It just gives you the result. It also gives you the parallelogram. It also gives you the ratio correction factor based on the test you do on a mirroring type CT. But it does not explicitly tell you, hey, this is a bad CT. You can determine based on the results you saw from the CT. Okay, for the concurrent saturation test, how do you test all the taps concurrently? Is it applied from X1 to X5? Please clarify the difference between concurrent and non-concurrent saturation test. Mr. Nicola Arnaut. Okay. So when you're doing a saturation test, you are applying, well, let's go back here. Saturation test. So what are you doing here? You apply voltage on the secondary winding of the CT, or you vary the voltage applied on the secondary, and then you measure the current flowing on each secondary winding. All right, so that's what you're doing. On a concurrent test, let me come back to this picture. So we have 5 voltmeters on this CT tester that measures the voltages across each and every single tap concurrently. So it's based on a calculation depending upon the ratio of the CT itself. So when the way you do it normally is you apply voltage, or in the older methods you apply voltage and you measure the current across each and every single terminal. Since we have 5 voltmeters present in each and every single tap on the CT test set, it is easy to calculate what would be the current and also what would be the voltage drop across each and every single tap. So that's one of the reasons why I include another slide saying that we did a test on concurrent and non-concurrent test to show you what is the difference between when you're doing a concurrent and a non-concurrent. We didn't see much of a change between the same test that we did. So concurrent test measures the current at the same time. Non-concurrent test measures the current individually. Even the concurrent test does it individually, but at the same time. Okay, so my last question, again, I see a lot of questions here. People want to ask me a lot of questions, so I'm going to respond to all the questions, each and every single question after this, because we are actually ran out of time. But I'll take another one question. This is from Mark Soper. What is the primary reason for ratio accuracy change in service? Magnetization, shorting of secondary windings, or something else? Well, I think you have answered your own question, sir. Yes, the primary reason for ratio accuracy is because of the change in the magnetization characteristic of the CT core. Sometimes when you look at a CT, it is just made of an iron core or some typically an iron core, and it starts to magnetize after a while because of high current or because of various reasons. And on top of my head, I can think of high current because of any fault. So so the primary reason for the ratio accuracy to differ is because of magnetization, and also I would add disintegration of the leads, the insulation of the leads. So as the time goes by, your insulation disintegrates, or there's a potential for the insulation to disintegrate, and that could also affect the ratio, because once the turns start touching each other, then you're pretty much losing the turns one by one. So that is also another reason. And there are lots of questions. Okay, all right. Again, for those of you listening to me, I really appreciate your time. Thank you so much. And I I'll hope to respond with all the questions. Sorry, I hope to respond to all the questions with answers as much as I can, and if possible, I will also ask some of the other people to give you a better answer than I can come up with myself. I really do appreciate if you can send us a feedback on how I did the presentation, and thank you so much for your time, guys. Appreciate it, and do join us for our next webinar.
Okay, and our next webinar is going to be, should be able to see on the screen, titled Application of Symmetrical Components and Relay Testing. That's going to be on January 20th at 10 a.m. Central Standard Time. The presenter will be Mohit, and he's one of our relay application engineers here at Megger as well. And also, again, sorry for not being able to get to all the questions. We ended up having over 40 questions, that's good. But we'll definitely be responding to those as soon as possible, so please give us a little time to get the best answers for you. But again, we want to thank you all for attending. We hope to see you again at our next webinar and some of the future webinars. We will be holding one every month this year. It's usually the third Friday of every month at 10 a.m. same time. So again, follow us on Facebook, LinkedIn to get updates on those webinars and when they're happening and the titles. Other than that, have a great weekend and a happy holidays, and please remember to answer the survey if you can. Thank you.